In this lecture, we are going to perform a nodal analysis of a circuit that has a voltage source in it. The voltage source does not make things excessively complicated, it is just going to replace one of our usual unknowns with another unknown. Let's begin by selecting our ground, which is the first thing we do for nodal analysis, as our 0-volt reference voltage. Then we will highlight our nodes. Let's call this one A and this one B. These are the nodes because they are the junctions that connect more than two elements of the circuit. In this case, they connect 4 each. I've labeled their voltages as follows, VA and VB. Now there's a few interesting things to notice about this circuit that will help us analyze it. First of all, consider the relationship between VA and VB. Pause the video now and see if you can figure out a simple mathematical relationship between VA and VB. Think. VA plus 2V equals VB. What this means is that effectively we only have one voltage unknown, VA, or VB, because if we knew VA, we would instantly be able to get VB. Secondly, what is the voltage across this 10 ohm resistor? Think. 2 volts, because it is parallel to this 2-volt battery. What this means, incidentally, is that we can instantly determine the current across this element of the circuit. It should be 2 volts divided by 10 ohms, or 0.2 amps. However, we do not know the current across the 2-volt battery, so we're just going to name that I. Notice what I'm doing here. I have not even started nodal or mesh analysis. I've just used facts I know about circuits to give me facts about different elements in the circuits. I notice there's a 2-volt battery. That means I can automatically set myself up a relationship between VA and VB. And also, because I know that these two elements are parallel, the battery and the 10 ohm resistor, I can set up a relationship between their voltages. I only do this because I have concrete numbers that enable me to get more concrete numbers. It's quite nice, or enable me to eliminate unknowns, like in this situation. Anyway, the reason I've said that this voltage is I and said it so specifically when all the other currents are technically unknown is because this current cannot be determined using the usual Ohm's law. There's no resistor in this area, so this I is really super unknown. I've labeled the other two unknowns in the circuit, I2 across the 2 ohm resistor and I4 across the 4 ohm resistor. Now that we have our nodes selected, it's time to write our nodal analysis equations, which is basically KCL at each of the equations. Note, VA and VB are not equal to anything necessarily in these equations. I'm just saying VA to denote that I'm focusing on the VA node. The currents entering the VA node are 2 amps and 0.2 amps, and the currents exiting the node are I and I2. The currents entering B are just I, and the currents exiting B are 0.2 amps and I4 and 7 amps. Now let's express I2 and I4 in terms of VA and VB. Based on the Ohm's law sign convention, because we picked the arrow for I2 downward, we should have the positive terminal and the negative terminal, which means that I2 is going to be equal to VA minus 0 over 2. Note that we subtracted the negative terminal's voltage from the positive terminal's voltage. Now, I4 is equal to VB minus 0 over 4, and because VB is VA plus 2, this is equal to VA plus 2 over 4. You see that I removed the VB variable because we know it can be expressed in terms of one unknown, and I don't want two unknowns in my equation when I could just have one. Now we'll begin to substitute. 2.2 amps on the left equals I plus VA over 2. Meanwhile, I equals 7.2 amps on the right plus VA over 4 plus 2 over 4, which is 1/2 or 0.5. So this can be rewritten as I equals 7.7 amps plus VA over 4. I'll multiply this equation by 2 to get 4.4 amps equals 2I plus VA, and this equation becomes 4I equals 30.8 amps plus VA. I'll subtract these two equations from each other to get 4I minus 4.4A equals 30.8A minus 2I. Notice that the VA's canceled out. We get 6I equals 35.2, and incidentally, 35.2 divided by 6 is not very good. Well, I just equals 5.867. We'll say that for now. By the way, it's worth noting that I'm absolutely destroying all the units right now, and they're very bad, but I'm just assuming that I'm going to get the right units. Sorry about that. Anyway, VA equals negative 7.333 volts, and VB therefore equals negative 5.333 volts, because as we know, VB equals VA plus 2V. Let's just confirm that all of this works in Kirchhoff's law. For VB, 5.867 equals 7.2 plus negative 5.333 over 4. This is roughly correct. Great! In VA, 2.2 amps equals 5.867 amps minus 7.333 divided by 2, which is also basically accurate, so another check mark. We have succeeded at solving this problem.